Let's see, making sure that audio is good, and it does look good. Okay. So let's move on ahead. I should be sharing my screen. That looks good. All right, perfect. Okay, so today's lesson is on 9.4, 9.5, inscribed angles and polygons, and angle relationships in circles. So you can go ahead and kind of just take your time and put all those notes in. And so we learned some new vocabulary, right? The first one being inscribed angle. And the inscribed angle is always on the circle itself. Okay, so that's a little different from the central angle, where beforehand we've seen central angles be in the middle. Say that this was our center, and this would be an example of our central angle. Okay. But of course, this is a little bit different than our central angle. This is what our inscribed angle is called. And our inscribed angle is on the actual circle itself. Then we have the intercepted arc, that's the arc in between. And then we have our subtend vocabulary term here, which I don't think we're going to use a whole lot. It's kind of just there to be there, I think, as far as I can tell. But it is kind of good to know that AC, the arc, and AC, the segment, subtend angle B. And I'm pretty sure that just means that it's just a part of it, right? It's in the middle of those two chords that are created there. Okay. So I don't think anything too intensive, nothing too hard or difficult to understand. Then we have our next theorem, in which our next theorem basically just says the arc measure is twice as large as the inscribed angle, or in blue here, in other words, the inscribed angle is half the arc measure. Okay, those are pretty much saying the exact same thing, just worded a little bit differently. Okay. So this blue one kind of corresponds to this equation here, whereas this red one is going to correspond to this kind of equation, 2 times the measurement of arc ABV, ABV equals 1/2, not 1/2, sorry, equals the measurement of arc AB. Okay, so those two are more closely related to each other as far as an equation goes. But we're going to use either one of these equations. I find it easier just to use the whole number 2. Just makes things easier on us. And so if I were to go ahead and move on to the next problem, right, we have some examples here. Okay, I would prefer you try to do example 1 first. Really, I'm going to show you how to do it. But if you're trying to do this on your own, I would do example 1 first, then we'll move on to example 1. Because those two are a little weird. Okay. Here we have to find the indicated measure. I'll do the arc DG in this kind of blue here. And what I'm looking for is this arc in blue. Okay, that's what I'm looking for. And so if I'm looking for an arc, that means I need to have an inscribed angle. Well, the inscribed angle is going to be angle E. And I know that because E is on the actual circle. And of course, it's an angle. And so everything in blue here is what is related to each other. So in words, what this would look like, it is 2 times the angle E, or the measurement of E, and that is going to be equal to the measurement of arc EG. So from here, plugging what we know 2 times 40 is equal to the measurement of DG, which therefore means that this is going to be equal to 80 degrees, and that's what DG is. Take a similar approach with G here. G is the angle. Oops, that's unfortunate. This is what I'm looking for right here in red. If I'm looking, if I have an inscribed angle, that's what I'm looking for, I must have an associated arc, and our arc, I just did it again. Our arc is going to be this EF right there. Okay. So we'll use the same equation just because it's easier with 2. 2 times the measurement of angle G is equal to the measurement of EF as an arc. We'll plug in what we know. 2 times whatever the measurement angle G is, we don't know it yet, equals the arc measure of EF, which is 58 degrees. We'll divide by 2 on both sides because that's how we isolate it. And we'll find that the answer is going to be 29 degrees. Just like that. Go ahead and take some time to see if you can solve example 1. And then come on back. I'll show you how to do part A, measurement of angle T. Measurement of angle T should have been the easier one. We're looking for this angle here, and we have this arc to help us find that. And so it should be pretty simple. 2 times the measurement of angle T is equal to the arc measure RS. And that is going to equal 2 times measure angle T equal 48 degrees. Divide by 2 on both sides. We get a final answer of 24 degrees. That should have been easy. Then the potentially more difficult part is I'm looking for QR here. Okay, well, QR is this arc. Okay, what I'm highlighting here in blue. That arc is a little bit trickier to kind of solve for. Okay, because I don't have an inscribed angle. I don't have QTR to be able to find that arc measure there. However, what I do have is angle QRT. And QRT is going to give me, let me make sure I can differentiate these colors. Angle QRT is going to give me this arc using this angle right there. Well, something that we should notice here is that TR, the segment TR, is actually a diameter. So TR segment is diameter. And something we need to remember about diameter is that it equals 180 degrees. And so if I know that arc TQ and arc QR add up to 180 degrees, I can find QT first, then subtract QT from 180. And that's exactly what I'm going to do. So in order to solve that, I need to first solve for QT. I'll do it in this green. I know I have 2 times the measurement of angle R equals arc QT. 2 times 50 degrees equals the measurement of QT, which means that 100 degrees is the measure of arc QT. Okay, pretty simple there. And then whenever I actually try to solve for my QR, I take the measurement of QR and put that equal to 180 degrees minus the measurement of QT. So measurement of QR equals 180 minus 100, which means that measurement of RQR is 80 degrees. And that should be pretty simple. Okay. Next, we have a turn to talk, which actually is not in either your key, key points and theorems packet or your work packet. So not that we're going to ignore this, but we're kind of just going to talk about this real quick. If we look at RS, which is this segment right there, or sorry, segment, this arc right here, we know RS has a inscribed angle U, and that means that we'll just take U and multiply by 2. So RS is 62 degrees. But if we're also looking for STR, STR is a completely separate angle. It's actually this red angle. But realize that it has the exact same inscribed or intercepted arc as the previous inscribed angle. And so what we'll find here is that we'll take the arc divided by 2, and we get 31 degrees still. And so essentially what we're going to get out of this is what's here on the board now. The minor arc, RS, is the intersected arc for both inscribed angles, RUS, and STR. Okay, so we would see that two things can be true at the same time. We will see another theorem about this in a little bit, but keep that in the back of your mind. The next one. Example 2, name two pairs of congruent angles. Okay, well, if you're a smart aleck like myself, I would say angle APB and angle CPD because those are vertical angles, or BPD and APC. Like, yeah, that makes sense, totally, for sure. But really, we're looking for inscribed angles, right? So maybe you should have said you're inscribed angles, just to be very clear what kind of angles we're looking for. But here, whenever you're trying to solve for inscribed angles, you got to make sure they have the same arc. So if I look up arc BD, right, which two angles have arc BD? Oh, it would appear that angle A and angle C. So angle A, current, angle C. You do the same thing for AC. AC is this arc right here. And it would appear that angle B and angle D are going to be congruent here. And that is correct. If we then move on to the next slide, it actually tells us exactly what we just said for the turning talk and for the previous example. Okay. In theorem 10.11, the main takeaway here is that the inscribed angles are congruent if they share the same intercepted arc. Okay, so I apologize for the kind of weird writing. I don't know. The formatting. There it is. Formatting. Apologize for the formatting. It's there. Okay. Definitely the most key takeaway from this. And then example 3 and extra example 3 should be really easy, right? We see that angle E is 75 degrees. Angle E has this arc here that's going to be its intercepted arc. And you'll see that angle F has the exact same intercepted arc, which means that angle F must be 75 degrees as well. Okay, that should be pretty easy, I hope. And well, you'll find the exact same thing for extra examples 3. Angle C is 68 degrees. It has that intercepted arc AD, and B has the same intercepted arc. Therefore, angle B is 68 degrees. Okay. So that should be pretty easy. Should be easy enough. Next, we have some new vocabulary here. Okay. We have what's called the inscribed polygon. Inscribed polygon is just the polygon on the inside. And then the circumscribed circle. Okay, circumscribed is on the outside. Okay, so make sure you know the difference. You can have any polygon in here. And remember, any polygon is defined as any three-sided shape, or really any three-sided polygon, or should be more specific. Because all polygons are three-sided or higher. And so we actually have some specific rules, I guess you can call it, or theorems, really is what they're called, for our right triangles and our quadrilaterals. Remember, quadrilateral is any four-sided polygon. And so in 10.12, basically just tells us if there's a right triangle, then the diameter is a part of it, and kind of vice versa. If a diameter is involved in a triangle, it's a right triangle. Okay, so either way you can say it, it's going to work. And then 10.13, you want to use the opposite angles. Okay, because opposite angles are going to be congruent to each other. So if you're in my class, kind of think back to what we talked about with the groups. If I was in one corner, then the opposite corner for me is going to be the one that's going to be supplementary. Okay, so make sure that you are aware that angle E is this angle in blue, angle G is this angle in blue. and those are completely separate angles. Okay, but they are opposite from each other. Therefore, they are supplementary. Okay, no longer are we doing consecutive angles because that's what we learned previously in Unit 7, but this is completely different now. Okay, we'll see some examples. We'll do this first one on the left. I have a diameter. I have some sort of triangle. And so it would appear that I have a right triangle because of the diameter is involved here. It's a triangle. And something to know about the diameter is the diameter is always the longest side. Well, if I'm dealing with a right triangle and a longest side, that's what I would call my hypotenuse. Okay. That's what I would call my hypotenuse. And the hypotenuse is always the direct opposite side from an angle, and that such angle is the right angle, which means that angle C is going to be a right angle for us. And that helps us here, right? If I know that the measurement of angle C is equal to 2x, and I know that the measurement of angle C is equal to 90, by transitive property, I would say 2x equals 90. Pretty simple. Divide by 2, divide by 2, x equals 45. And that's my answer. Then for B, remember my opposite angles, not consecutive. So D and G are not opposite from each other. They might look opposite from each other, but they're consecutive. They're right after one another. Because they're right after another, we can't use them. But we know that D and F are going to be supplementary. So the measurement of angle D plus the measurement of angle F is 180 degrees. Similarly, how the measurement of angle G plus the measurement of angle E supplementary. And we'll just solve by plugging in those parts. Measurement angle D is Z degrees plus the measurement angle F, which is 80, equals 180. Subtract 80 on both sides, get Z to equal 100 degrees. We do the same thing for G and E. G is Y degrees plus E, which is 120, equals 180. Subtract 120 on both sides. Y equals 60. And that is my answer. Pretty simple. Okay. Go ahead and try this on your own first. See how far you can get. Come back if you are confused. Let's go ahead and get it. Here I have a diameter, which means my diameter is my hypotenuse, which means that the opposite angle is going to be my 90 angle. I get 5x equals 90. Divided by 5, divided by 5, x equals 18. And that's it. Problem's already done. Similarly, for part B, I need to know that my opposite angles here are in fact still opposite. So although D and E are on opposite sides of the circle, they're not opposite sides of the polygon inside. Okay, so we can't use D and C, we have to use D and B. So measurement of angle D plus the measurement of angle B equals 180. Same thing with the measurement of angle C plus the measurement of angle A is equal to 180. So D is 3A plus B, which is 111, equals 180. 3A equals 69 because I subtract 111 for both sides. I get 69 divided by 3 on both sides. A equals 23. Now I'll solve for B. C is 65 degrees. A is B degrees equals 180. Subtract 65, not 160. 5 B is equal to 115. That is that. Okay. Should be pretty good. This was our do first for today. So I might as well just go ahead and cover it real quick, just because I think it might be good for us. Remember in 10.3, or sorry, 10.7, the theorem 10.7 is that whenever we have a diameter intersecting a chord at a 90-degree angle, meaning that they're perpendicular, that means that the segments created from the chord are congruent and the arcs are congruent. So, which means I can put 2y plus 1 equal to y plus 4, and I subtract y's. 1, I get y equals 3. I plug 3 back in, I get 7 for each side, 14 for the whole chord, but it doesn't look like I'm looking for the actual chords or arcs. I'm just looking for the x and y value, but that's how you can check it. Same thing with 5x minus 18 equals 3x minus 4. 3x, 3x, add 18, 2x equals 14, 5 by 2, x equals 7. And you can confirm that if you subtract, if you multiply 7 into 3 and 15, or 3 and 5, you get 21 and 35. Subtract 4 minus 18, you get the same number of 14. Okay, so this is correct. Okay. Then we have another problem. Another problem, key point. The next key point is true only whenever tangent and a chord intersect. So they have to intersect at the point of tangency. And basically just says that the arc is always twice as large as the angle created from the chord and the tangent. Okay, that is the best explanation I've been able to say. So in this case, right, if we're looking at this angle 2, well, times 2 is equal to the arc. The same thing is true the other way around. If I have arc AB times 1/2 is going to equal my angle 1. And you see it right here on the screen here, right there. Okay, so make sure that you understand that part. And then we'll go ahead and use that here, right? Using this idea, this theorem here, I'm going to take 130, right? It's my arc, which means I want to have my angle. My angle is half the arc. So 130 divided by 2 equals the measurement of angle 1. And I just saw it. So the measurement of angle 1 is equal to 65 degrees, because that's what 130 divided by 2 is. Okay. A lot of the time, it really is this easy, right? Especially for these kinds of theorems. A lot of it is easy, just making sure you know what to plug in and where. Okay. But for B, for instance, I have the angle. Okay. Well, if I take the same approach, I take 125, which is my angle, I put that equal to the arc, in which case what I'm looking for is the measurement of arc LJK divided by 2. Well, the opposite of dividing by 2 is multiplying 2. Okay, those will cancel. I multiply by 2. That then means that the arc measure of LJK is equal to 250, not 225, 250 degrees. Okay, go ahead and try to solve the other two. And come on back. Same thing, I have an arc here for 240. I'm going to take 240 divided by 2. Oops, that's a terrible way to put it. You can divide by 2, you can multiply by 1/2. They're both the same thing. I get the measurement of angle 1 to equal 120 degrees. And part B, I have the angle, I want the arc, I'm going to multiply times 2, and I get the measurement of arc LJK is equal to 310 degrees. That should be pretty straightforward. Oh. Okay. last couple of points. I think I have like 4, maybe 5 more slides left, and I have about 60 minutes. I should be fine. Okay. Here, this is kind of just going over stuff that we'll find on our reference sheet. Okay, make sure that you know this for sure, that it's on your reference sheet. It's right under the right triangles. It says circles. You can't miss it. Okay, because you don't have to memorize this. Okay, this is the easiest thing, because you don't have to memorize it, right? That's the good thing about having this reference sheet, is that you don't have to memorize some of these equations. Okay, and quite frankly, these are not that they're necessarily hard equations to memorize, but they are kind of, what's the word? They're just not nice to memorize. Okay, so it's good that we have them available to us already. But the important thing, now that we don't have to memorize these, is being able to identify which one to use and why. So if we look at 10.15, it's angles inside the circle theorem. Specifically, angles inside the circle. Okay, that's when we're going to use this one. And notice, what is AC and BD? Those are chords. So this one, you're going to write chord for. Because if you look at your reference sheet, right, of course, if you're at home, you might not see it. If you look at your reference sheet, you'll find that there is a 2 chords kind of box under circles that you can use. And this is the exact same thing that we see on our screen here. So we'll write chord. Theorem 10.16, however, is on the outside. So angles for the outside of the circle. And notice here, AB is a line, really it's a ray, but there's no point here. Okay. AB is a secant, whereas C is a tangent. Okay, again, you'll find this in your reference sheet. It says tangent and secant. Well, go to the middle one. This is obviously a tangent, so write that in for your notes. Tangent. And there is a box for the tangent. It's called 2 tangents. And the last one we have is secant. Secant. And that, of course, is on our reference sheet. Again, you're going to use each of these equations for the specific combination of secant, tangent, or chord that you'll find in your circles, okay? You must be able to identify that. If you cannot, you must practice. Okay? So, with that in mind, we'll go ahead and kind of look at this. We've already kind of seen this, right? We already know our inscribed angle is on the circle. And then from the previous 2 theorems, we can find our inside and our outside angles from the theorems that we just learned. So that's just kind of a good kind of recap. But then now we have the actual like meat and potatoes of this kind of section here. So we have example 6 and extra example 6. Try extra example 6 on your own. I'll go ahead and do example 6. Now here I'm dealing with a chord and a chord, which means I have my inside angles. And in this problem, I must say that the measurement of angle x. Okay, notice I'm using angle x only because this is what I'm looking for. Okay, I would have called it angle z, or the 3-letter parts. Actually, no, we'll just go with that. We'll say that the circle has an intersection at z. Okay, that is that intersection. And I will say that the measurement of angle KZL. Okay, just so there's no confusion as to saying measurement of angle x, because I've had students already confuse measurement of angle x with other problems. Okay, do not confuse that. The measurement of KZL is equal to 1/2, and I'm just following the notes, or sorry, following the reference sheet, is 1/2. In this case, it says AC for the reference sheet, but notice that AC is the arc for angle 1. So the arc for angle KZL is arc AL. And it says plus, and notice that on the reference sheet it says DB. Well, DB is the opposite arc from AC. So the opposite arc of KL is JM, measurement of JM. And I'll plug in what I know. I don't know what this is. I'm going to replace it with an X. That's what I'm looking for, X degrees. equals 1/2 times KL, 156, plus JM, which is 130. We're just gonna combine like terms. I add those two up, I get 286. Divide by 2, I get 143. And that is what x equals. That's it. That is it. And for part B, I of course have a tangent and a secant line. So I gotta use the tangent and secant. And what this one tells me is that measurement of angle C, right? C is the outside angle. Measurement of angle C is equal to 1/2 times, according to the reference sheet, AD, which is the larger angle. AD in this case, of course, is also our larger angle, so measurement of AD. Not plus, it's a minus. My mistake. It should be minus. AC, which was the smaller angle, which in our case is getting the measurement of BD, our angles. Okay. And so I plug in what I know. X degrees equals 1/2 times AD, which is 176 or 178, minus BD, which is 76. I subtract 178 minus 76, I get 102, multiplied by 1/2. That's going to give me 51 degrees. Okay. Now that you've tried to do example 6, example 6A in particular is a much, I would say, much more difficult kind of question, only because some students, and by some, I mean a lot of my students, couldn't catch the trick at the very front. So notice here, I do have 2 chords, which means I'm going to use the same theorem as I did in 6A. Okay, but I have 2 of my arcs. But what I'm missing is actually the angle. So if I were to set this up, I'm going to say the measurement of some angle, I don't know what it is equal to 1/2, right? Because I don't have any letters, I'm just going to go ahead and put the numbers in. 1/2 of 80 plus x. Well, that's a little bizarre, right? We can't figure out nothing, right? But on the contrary, what we're missing here is the angle. And remember, any straight line is always 180 degrees. So if I know that this 94 here exists, and the angle next to it is the linear pair with it, that means that this angle has got to be 180 minus 94, which of course that is going to equal 86 degrees. So I have the 86 degrees. I'm still trying to find my x, right? Replace everything. I'm going to put this all in terms I can read. And now it's just an algebra. Here, you can multiply the 1/2 through, distribute it through. I don't recommend it. Just multiply by 2. It cancels the 1/2, puts the 2 on the other side, multiply the 2 into 86. You get 172 equal 80 plus x. Then you subtract, get x equals 92 degrees. And that is for your arc. Okay. More difficult, but once you see the trick, you probably will never forget it. Now for B, however, we have 2 secants, so we'll follow the same theorem. In this case, I have the measurement of angle A equals 1/2 times BD according to the reference sheet, which is the outer, I guess, outermost arc. In this case, is going to be CE plus, not plus, sorry, minus the inner arc, which was, in our case, BD. And I'll replace. I know we have 35 degrees equals 1/2. CE is 100. BD is x. I'll multiply the 2 here, cancel out. Get 70 equals 100 minus x. Subtracting 100 on both sides. Negative 30 x. X is going to equal 30. That is my problem. Okay. Last little bits of notes. We have a key point left and a theorem. Key point 6 talks about a circumscribed angle. It's an angle whose sides are tangent to a circle. Okay, so this is just a tangent. So going back to what we talked about here, where we have a tangent in the middle, this actually makes things a little bit easier for us, but with a catch. Okay, in this theorem, it says we can figure out what the actual angle on the outside is if we know what the central angle is. But if we don't know what the central angle is, we cannot figure this one out. And we'll see some examples of these. We'll see some examples of both, actually. So going forward, example 7 and extra example 7 should be pretty easy. Okay, we know that they're going to be easy because we have a central angle and we're looking for the outside angle. So we'll say that the measurement angle D is equal to 180 minus the measurement of angle ACB, which of course is just super straightforward, like so. Measurement angle D is equal to 45 degrees. Same thing with X, or same thing with extra example 7a. Okay, I'm not going to do the whole thing over again, but I'll say that the measurement S with 180 minus 4, measurement of angle S is equal to, oh, do the math, 56 degrees. Those are our simple problems. However, B and both parts are going to be our more difficult problems. Okay, and we'll try to get through those as best as quickly and as accurately as we can. Now here, we can't use the central angle trick. And actually, if we look at our tangents on our circles reference sheet, we actually can't use our tangent either. But that's okay, right? Angle J, where we have our X, is our inscribed angle. Well, remember the inscribed angle, J, in our case, right, measurement of angle J, is equal to 1/2 of its intercepted arc, in which case this intercepted arc is EF. Now, ordinarily, that would be good, right, if we had the arc EF, but we don't. But we can figure it out. Okay, visualize this with me. If I know EF is the arc I'm looking for, I know for sure that there's a central angle that I can solve for. I know that for sure. Okay, and remember, central angles equal its arcs. And so if I know that EF is my arc and EF equals its central angle, then I can find its central angle. Look back at this theorem here. If I were to rewrite this, right, ADB is the outside angle equal to 180 degrees minus the central angle. Well, if I already have my outside angle 30, I can solve for my central angle and rewrite this equation as central angle equals 180 degrees minus my outside angle. And that's exactly what I'm going to do. I know that EF, measurement of EF, is equal to angle G, right? The angle that I created here. Well, I also know that angle G is equal to 180 degrees minus angle H. And because this is true, using transitive property, measurement of measurement of EF is equal to 180 minus angle H. Measurement of angle H, I should say. Putting all those measurements there. So now I have a way to solve this. The measurement of angle J is equal to 1/2 times 180 minus the measurement of angle H, which then gives me 180 minus 30, which then equals 1/2 times 150. Therefore, measurement of angle J is 75 degrees. Okay, boom, math. Love it. We'll do the same exact thing for part B in extra example 7. To a T, the exact same thing. But I'm gonna do all that work again. I'm gonna just skip right to this step right here, just because I'm a little short on time. But I know that I'm looking for the measurement of angle C equal to 1/2 times 180 minus my outside angle, which is the measurement of angle D. And so I would replace the values in measurement C equals 1/2 times 180 minus 42 degrees, 1/2 times 38, 1/2 times 138 equals 69 degrees, and that is what the measurement C. Okay. Don't forget, you should box your answers. I'm just doing it for emphasis. Okay. But that is it. Like, we're done with 9.4, 9.5. It felt like it took forever. Okay. If you were here for Tuesday, don't forget you have an exit ticket. Make sure you come in during tutorials to come and take that exit ticket. But otherwise, that is the end of today's lesson. And if I haven't seen you already, I will talk to you all later. And if I do see you later today, rather, I should say, then I hope you are ready to learn. Okay. Alrighty then, I will let y'all go. Bye-bye.